consider is the viscous drag force. Viscous drag force from, so there's a drag force, and this is from the air. So the space between these two plates is a space. Okay, so once the space is just filled with gas or air. So once you have an object that is traveling through an air, there is going to be an air drag on it. So which is serving as what? A frictional force to that moving object. Okay, so we have an air force or air drag on it. Okay, so the air drag is the droplet falls through the droplets falls through the air when the electric field is turned off. Okay, so when there is no electric field, remember I said that the electric field provide a force that is counteracting the gravitational force. So the moment there is a zero electric field, then there is no force that will be preventing this charge from dropping or coming down to the second plate. So the moment there is zero electric force or field, then the droplet will discharge or detach itself from the upper plate and then falls to the next one. So the moment we switch off the electric field, then there won't be any opposing force again, and the particle is going to move freely. Through the only force that will be opposing will be when it leaves the plate and it's down within the space between the two plates. So there's going to be an air drag force there that will also be slowing down that object or the oil drum. Okay. So when it's turned off now, the air drag pushes. The air drag pushes upward against the moving droplet. So, and this is governed by the Stokes law. So the Stokes law is saying that the force of the air drag is equals to 6 pi newton, then R V, where the newton here is the viscous coefficient, then the R is the radius of the drop, then we have V as the velocity of the drop. Okay, so we have this. Okay, so here I didn't give you the expression of the force. So here the electric force, let's say that one is Fe. It will also be equals to the charge times the electric field. So let's give this one as the second force. Then the third force will now be the air drag. So 3 here. This will be the third force. Now, when we apply these 3 forces, then we will be able to determine the elementary charge value, which is the 1.6 times 10 to the power minus 19 coulomb. So these were the things that he considered and then came out with that value as the electric charge. Okay, so let's now see how we can calculate that charge. So we said that the electric force is the same thing as equals to the gravitational force, that's Fg. So that balances the gravitational force. Now, we can equate these two, that's equation 1 and then 2. So it means that we can say that Q E is equals to mg here. So that is the expression for that. Now, we also know that the electric field is equals to the voltage times voltage divided by the length or the distance. So the distance of the chamber. So let me put that one T here. So this will be the electric field. So if this is equation 4, then when we substitute the equation 5 into equation 4, so it means that we can say that our Fe, which is the left-hand side of equation 4, is the same thing as Q, V, and then divided by D, sorry. This is equals to mg. Okay. So we made an assumption. So at the balance point, this is equals to that. So at the balance point, the electric field is the same thing as the gravitational force. Okay, so we can make the charge the subject from this expression. So making charge the subject, we say that our Q will now be equals to m chain multiplied by D over the V. So let's give this equation as equation number 6 here. Okay. So now, also from the third force that we saw, that's the Stokes law. So we are saying that from the Stokes theory, from the Stokes law, we saw that the drag force, which is Fd, is equals to 6 pi neta r and then V. Okay, so now we also saw that I also explained that the moment the charge is dropped or detached from the upper plate part, then there is going to be an opposing force, which is the air drag, because the charge will now be moving down or accelerating down in between the space here. And this space is filled with what? Gas or air. So we also obtain that force or air drag from the space between the two plates. And that is going to be serving as a frictional force. It will be serving as an opposing force to the force of gravity. So we can also equate those two forces. So just think about an object that is moving on a horizontal rough surface. Okay, so if you apply a force like here, this is the direction of your applied force. Then because this surface is rough, then you're going to have a frictional force that will be opposing this applied force. So in the same way here. So the applied force here will be your gravitational force, which is going to be the force of gravity pulling this charge down. Then because there is a force, air drag within this space, will also be opposing this. So we can equate those two forces too for the particle to be balanced. Okay, we can equate those two forces. So we are coming to apply the same concept here to the Stokes law. So it means that we can say that the F chain is equals to the FD. And then F chain is M chain, which is equals to 6 pi nature, that's the coefficient of viscosity, times the velocity, R times velocity. Okay. Now, we know from basic principle that density of a substance is equals to the mass of that object or substance divided by its volume. Okay, so which means that the density rho is equals to mass on volume. So now we have mass in this equation here. So let's say equation 7. So we can make the mass the subject here because the mass of the drop was not able to determine, but we can get the velocity and the volume and the substitute in place of that. So we make M the subject from this expression, the density expression. So in doing so, we have our mass to be equals to the rho times the volume. So that is the mass of that. Okay, so we can substitute this one into our equation 7, that is here. So by doing so, we substitute the M in the mass here. So if you do that, we'll have our mass to now be equals to rho V chain to be equals to 6 pi, the coefficient of viscosity times the radius times the velocity. So let me use these terms so that we differentiate between the velocity and then the volume. So let me say where I wrote the velocity first. So let me make this one V subscript D so that we know that is the velocity of the drop. Since we have volume and they're all VV, we may not make the distinction between the two V's. So let's say that VD is the velocity of the drop. So wherever we see VD, it's velocity, but the normal V is just volume. Here, this is potential, so forget about this. The capital V here is potential. So this is potential. Okay, so here we make this VD. VD here. Okay, so now we have this VD, and this is now volume here. Okay, so from here, we can now make the radius the subject if we want to calculate for the radius of the sphere. We can make that one the subject. So we know that the drop is spherical in shape. The drop is spherical in shape. So what we'll do is that, so let me say, since the drop is spherical, then to find the volume of a sphere is always equals to 4 on 3 pi r cube. So that is the volume of finding a sphere. Let me fix it before it goes off. Okay. Okay, so we can substitute this one back to this equation here. So if this is equation number 8, then in place of the volume of the sphere, we'll put 4 pi r cube there. So it means that we're going to have rho, and then, so let me say 4 on 3 rho, then we have pi r cube, then multiplied by g, and this one will be equals to our 6 pi rho nu r, and then vd. Okay, so we have pi at both sides of the equation. We can cancel it out. We can cancel this term out. This term will also go with this. Okay, so now let's go back and check our Q expression here. We have the Q expression to be mg d over v. So make substitution for the mg, which is the mass. So we can do that here. So here, if we take 2, will go here 2 times, and 2 will go here 3 times. So this 3. So we now have 2 out of 3 rho r. Now this r will take away one of these r here. So this one becomes square. Then we have chain to be equals to 3 nu v d. Okay, so this is what we'll have. So we can make G in the subject from this expression and then see what we are going to have at the end. So making G in the subject here, so it means that we're going to have 3 times 3 will give us 9. So that would be 9 nu Vd. So Vd all divided by 2 rho r squared, and everything here is equals to G. So this is equation number 9. So if you substitute equation 9 into the charge expression here, that's equation 6. So if you do that, we'll have where we have our mg. Okay, So if we do that and simplify, we have this expression here. We have the charge to be equals to, we will now have 4 pi, then we have R keep, and then rho, we have chain D, sorry, R all divided by 3V. And when we substitute the constants of today's expression here, then we'll get our charge, which is the electron, to be equals to 1.6 times 10 to the power minus 19 coulomb. So this is how the elementary charge was found using this method. So they have to consider the forces that are acting on the oil that is dropping from the upper plate to the lower plate. And by considering the Stokes theory, the gravitational force, and then that of the electric force, then you have this.
Hello, sir.
On microphone is on.
Sir.
Yeah.
Where you started doing the cancellation, the 413 rho pi r cube g equals to that. It's like I'm lost a little bit. How did you get a 2 on 3?
Okay. So let's come up here. When we got these forces, that one there, you are clear with that?
Yes, please.
Okay. So here we are saying that the volume of the sphere, when the drop is spherical, the volume of a sphere is defined as 4 on 3 pi r cube. Okay.
Yes,
so
sir.
But the equation 8, we have the density times the volume times gravity. So if we substitute this expression here in place of the V in equation 8, we have our 4 on 3, then the rho here, we have our pi r cube, then times the gravity. But that is the same thing as the Stokes theory or law. That's the drag force.
Okay.
Okay, so if we have 4 on 3 and then 6 at both ends of the equation. So we divide 4 by 2. 4 by 2 will give us 2, right?
Yes, please.
So that's why we have these 2 here. And then when we also divide 6 by 2, we'll get 3.
Okay.
So we'll get 3. So now, if we make the subject here, what are we going to have? We have 3 by 3, that would be 9. Oh no, let's make R the subject here. This one should be R the subject here. So you make R the subject here. What are we going to have?
No, sir, please.
Yeah.
What I want to ask is that the cancellation. Were you having in mind that you want to get 2 on 3, or it was?
No, it's just like I am just reducing. If you want, you can just go straight to multiply.
Yeah.
3 by 6 to get 18 and you by 4.
Okay.
That one is not anything beyond.
So when you do that way, does it hold?
Oh yeah.
Okay.
You can multiply 3 by 6 and divide it by 4.
Yes.
So when you do that, you get 9 on 2, right?
Yeah.
because if you multiply 3 by 6, you get 18 here. Let me write it here, 18. Then you divide by 4. And this one can be broken down into 9 and 2. That is 2 into 4 will be 2, and 2 into 18 will give you 9. So you come back and then have 9 on 2 here as we are having here. Is this clear? Or so what I did here, it is not any special, it has no special meaning. Let me just put it that way. Is that like simplifying the terms here? So one can decide to multiply the 3 by the 6. So that will give the person 18. And then he will divide by 4. And the person will come back to the expression that we have here. I don't know whether you got what I'm saying. Okay, so forget about this. Your final expression is just the most important thing. And then we want to say that from here, from this equation, that this value was found. And this is what we have as the value for our electric field. Sorry, charge. So the elementary charge that we normally use as 1.6 times 10 to the power minus 19 came through this experiment performed by Millikan's using the oil drop method. Okay, so that is some of the discovery that we talked about last week that gave birth to the modern physics that we are doing today. So with the classical mechanics, the charge, it was difficult for them to quantize the charge, to see that charge is a discrete multiple of numbers. So we are seeing charge as what? A continuous thing. But with the development of the modern physics, now this experiment was able to better explain that charge indeed is what? A discrete number. Okay, so the next thing we'll be looking at is photoelectric effect. So this concept too was not able to be understood through the classical physics. So it was the modern physics that gave a vivid explanation to this. So here we'll be talking about the electron emission. Okay, so when you're talking about electron emission, you can have it in two aspects. The one is the photoelectric effect, and then the other one is the ionic or thermionic emission. So the thermionic emission is the use of what? Temperature or heat. So when you're using heat to remove an electron from the surface of a metal, in that case, you are talking about ionic or thermionic emission. But when you're using electricity, then you will be talking about the photoelectric aspect of the emission that is happening. Okay, so under the photoelectric effect, we have some method of emission that happens. So method of emissions. So the first one, the first method of the emission is the term ionic. Some people call it thermionic emission. Now the thermionic emission here, so in this type of emission, so there is the thermal in heat. Flow of charge carriers. Of charge carriers from a surface or over a potential energy barriers. So one thing you should just know here is the thermionic has to do with heat. So once you hear the word thermionic emission, it means you're using heat to remove an electron from the surface of a material. So here we are saying that the thermal energy is given to the carriers. To overcome the work function of the material. So the second, we'll talk about the work function later on. Every material has its work function, and then the work function tells the amount of energy that the material requires before it can liberate an electron from it. Okay, so we'll talk about it later. So the second one is a secondary emission. Secondary emission. So for this one, the electron gain enough energy by transfer from one electron to another of higher speed particle that strikes the material from outside. So what this is telling us is that when you have a fast moving object or electron striking the material, then it is able to cause an electron to be emitted. Okay, so that's the secondary emission, and that is caused by an object that is moving with a higher speed or velocity, and this object happens to collide or strikes the surface of that material. Then it causes the charge carriers within that material to be able to remove from the surface of that material. Now, the third emission that we're talking about is the field emission. You can also use a field. That is not necessarily by touching the material, but you can use a magnetic field or an electric field to also cause electrons to be moved from the material. Okay, so for the field emission, we are saying that here, yeah.
Please, can you touch on the secondary emission for me?
Okay, the secondary emission is a kind of emission that if you have a fast moving object like an electron or a photon that is coming from a different source, and this photon happens to have a higher energy. Okay, so once it has a higher energy, when it strikes the surface of that material, and the energy that the photon is carrying is greater or equals to the work function of the material, then it is able to create electrons or to remove electrons from the surface of the material. So the secondary has to do with something that is coming from outside. It is not happening within the material. Okay. So that is the secondary. So that one has to do more on photoelectric effect, that you have a photon that is coming out from a source, and this photon happens to collide or strikes the surface of a metal. The moment this photon has a work function, it has an energy which is equal to the work function or greater than the work function of the material, then it creates or it removes an electron from it.
Okay. So it means that when the photon is coming with an energy and the energy is lesser than the
Okay.
work, that one, what will happen?
Okay. So once the energy is less than the work function, it just strikes, but nothing happens. It doesn't emit an electron.
Okay.
You only emit an electron when you have energy more or equals to. They're like where you are, wherever you are, your station, and you want to come to UCC here. I'm just using this scenario, this layman example for you to understand. So you want to come to UCC here, and let's take it that where you are to this place, the lorry fare is maybe 100 cities. So when you get 100 cities, you'll be able to get to, let me say, the station in Cape Coast here. Then from the Cape Coast station to UCC campus is like maybe 10 cities. So it means that for you to be able to move from wherever you are to UCC, you need 110 cities. Now, I want to talk about when the photon energy is equal to the work function. So now, if they're giving you a money of 100 cities, so 100 cities means that the money that they've given you is equal to the lorry fare from your station to Cape Coast, no UCC. So that is the work function. So that money should be able to carry you to Cape Coast. Now, if you have more than 110, okay, so it means that you should be able to move from where you are to UCC campus. But if you have, no, okay, let me just take it like, yeah, that will, it will work. So, but if you have less than 110, no, less than 100, there's no way that you'll be able to move to UCC. So it means that the energy that the photon is carrying is lower than the wave function. So you cannot come unless you, so that one, you cannot, perform your mission. Okay, so if the photon energy is lower than the wave function of the material, nothing happens. It only strikes, but it cannot remove the electron.
Okay. Thank you, sir.
All right. So the field emission here is when we use a strong external electric field. Okay, it can be an electric field, it can be a magnetic field. So this is which strong electric, so this switch strong electric field pulls the electron out. Pulls the electrons out of the material. Okay. So let's now talk more on the photoelectric effect. So for the photoelectric effect in this, incident light into bracket energetic radiation shining on the material transfers energy to the electrons. Energy to the electrons, allowing them to escape. Allowing them to escape. So the ejected electrons are called so let's say this one, because I'm saying that the ejected electrons are called. So let's say this the particles so particles are called electrons. Let's move this way. Okay, so in short, you can just say photoelectric effect is the removal of electrons from the surface of a metal or any material at all, if light of sufficient energy falls on it. Okay. So we're saying that in this so for the electric effect in this incident light, that is energetic radiation shines or shining on the material transfers energy to the electrons, allowing them to escape. Okay. So this is what happened if you have a light source here, an electric source here. So let's say this is an electric voltage. I'm going to draw my lines. They are not straight. Okay, so this is connected to target here. And this one to a collector. So here, this is a collector. And this would be the emitter plate. So here, we put a vacuum here. Okay. So let's say we have light that is incidenting on this target here. So this is the incident beam that is coming in here. Now this will emit, when it touches this target here, it will emit an electron here. And this electron will be collected by the collector. So we are saying that this is the emitter particle, and here is the incident light. Okay, so we have here as the vacuum. This space here is a vacuum. Then we have our power source or supply. So this is a DC power supply. So DC power. Okay. So you have something like this. If you have your material surface like this. So this is a material. Then you have your incident light striking on this material. So this is the beam that is coming. Then it will reflect the electrons out like this. So this will be the ejected electrons. Then here will be the incident light. So in other words, the photon. No, light is a photon. So this is what is going to happen. Now, the equation that is guiding this is the Einstein photon equation. So it says that the energy that the incident light is carrying is equals to HF. So this is the photon energy equation. Or yeah, energy of the photon. Let me just make it in short. Energy of the photon. Of the photon. So here, the E is the energy of of the photon. Then the h is the Planck constant. Then the f is the frequency of the photon. Please, you take notice of this. The h, we have h and h bar. They are not the same thing. You have h and then h with a bar cross. They are not the same thing. Take note of it. H bar is equals to h on 2 pi. Okay, so if you take, h, and I'm writing h bar again. If you take the value of h divided by 2 pi, that will give you the h bar. And this h bar, we call it what? The reduced Planck constant. So when you are solving for the energy of the photon, they will give you the constant of what? H and then h bar. Don't go and pick the value for the h with the bar cross. When you use that constant value and solve it, you get your answer to be wrong. So use the h bar, like the h without the bar. Okay. So don't use the h bar when you are calculating this. So this h value is 6.62 times 10 to the power minus 34 joule second. Yes.
Okay, to say,
Yeah.
Concerning the photoelectric effect, can
Mm-hmm.
we say the electrons are, for instance, when the UV rays hit on the surface of roofing sheet and you
Okay.
stand at a distance and you see the radiations, that radiations, can we say they are the electrons ejected?
Yes. The radiation can be termed as the electrons in some contexts. Yeah. So when you are talking about the inverse of photoelectric effect, for instance, in that case, you have a fast-moving electron that strikes the inner part of an electron. So electron from a higher energy level has to liberate energy in the form of radiations to be able to occupy the space that is being created by the the photon. Okay, so you can, some context you can tell as that is the electron, but we have the radiations, which is a form of energy. Okay, so that one is an energy that is coming out. So you can use it as electrons for certain contexts, but you cannot just presume that the radiations that are coming out are the electrons that you are seeing. Is that okay?
Okay, sir. And concerning the Einstein's equation, the E is equals to HF.
Mm.
E stands for energy, F, the frequency, the H, the Planck constant. Why did he introduce that constant there?
Yeah. So in a discovery, you are finding a relation. So you want to find out what are the dependence of what you are looking for. So he realized that if you take the frequency of the photon that you have, when he incidented the photon on the surface, then he realized that the photon need a certain amount of energy so that it can be able to remove the electron from the surface of that metal. And he has been multiplying the frequency of the photon with certain numbers. Okay. And finally, when he uses, or when he used the value of the Planck constant, then he realized that the energy that the photon is coming with is the same thing as the frequency that it has with the Planck constant. So that one is just a constant value that is there. Is that like you try to see, you are comparing two things and you start multiply by 1. When you multiply by 1, it's not equals to what you want. Then you move to 2. It's not equals to what you want. You move to 3 until maybe you get to a certain number and it is exactly as what you want. So you can form your equation or your relation there. Is that okay?
Okay,
So
sir.
he tries several values and it doesn't work until this value work for his experiment. So that is why he concluded that since the constant is already there, so when you know the frequency of the photon, then you multiply by that constant, then it gives you the energy. And discovery is not something that is permanent. Somebody can also rely on this equation and also try to formulate another theory or equation based on the Einstein energy relation that we've seen here. You can also compare the Einstein relation equation. Maybe the particles that are emitting are also something in relating to this. So you can also build on that. Okay, so you can also write the equation in terms of the frequency. Okay, in terms of the speed of light, because the photon actually is light. So since c is equals to f lambda, okay, so means that here our f will be equals to c on lambda. So you can also write this same expression as hc on lambda. So where c is the speed of light, then the lambda here is the wavelength. So you see that the wavelength and then the frequency are inversely proportional. So when you have a light that has a longer wavelength, then it will have a lower energy. And this should tell you when you are dealing with your spectrum, where you have the X-rays, so you have your gamma rays, you have your X-rays, you have your radio waves, and then that down to the microwaves. So it means that when you arrange these things like this would be in decreasing energy. Okay, because the energy of the gamma rays is higher than the energy of the X-rays, which is in turn higher than the energy of the microwaves or the radio waves. So it's going to be in decreasing frequency. In other words, decreasing energy. But it's going to be increasing wavelength because the wavelength of the microwaves is longer than that of the X-rays and it's also longer than that of the gamma rays. So you can use this one to be able to arrange terms, the spectrum, to know which one has the highest energy, which one has the lowest energy. If you know the arrangement, which one comes before the other, okay, then you know their wavelengths or their frequencies. Okay. So now, if the photon energy is high enough, so if the photon energy is high enough, we will now have. So if the photon energy is high enough, then it should be able to remove the electron and then give the electron some amount of energy to move with. Okay, so in that case, you have your HF, which is the photon energy, to be equals to phi plus Ke. So let me attach this one so that you know. So I can say that E is equals to HF. Now this one will now be equals to, so here your phi here is the work function of the material. Then the Ke here is the kinetic energy of the electron. Okay, so when the photon energy is very high, then that is, if the photon energy is greater than the wave function of the material, after it creates or it removes the electron from the surface of the material, it transfers some of the energy to the electron to also move away from the material. So for instance, if this is my material and the electrons are residing on the surface of this material like this. So let's say this material has a work function of 2 electron volts. So phi of this material is like 2 electron volt here. So if a photon is incidenting on this material, HF, with, let's say, 3 electron volt, you see that 3 electron volt is greater than 2 electron volt. So here. So once this is greater than this, then it will remove the electron from the surface of the metal and gives this electron kinetic energy to also move away. But if the photon energy is 2, so if 2 is equal to 2, it will only remove the electron from the surface, but that electron will still be residing on top of the material. So you create the electron, but the electron will still be sitting on it, though it is loose. It's like you put something on top. But don't forget that these electrons at the initial stage are bonded. They are part of the material. So when the photon strikes it, then it removes the electron from it. That is, if the energy of the photon is equal to the wave function. So you only remove the electron, and that electron will still be on the surface of the material. But if the photon energy is higher, then this electron that is removed from the surface of the material will move away from it because it will get enough energy. The remaining energy is what it will use as a kinetic energy of the electron to move away from it. So that is why we are having this equation here. So HF is equals to the work function plus the kinetic energy. Okay. So that is the. So we'll talk about something we'll call stopping potential.
Please, just a quick question, sir.
Okay.
So there's a difference between remove and move.
Yes.
Okay.
Remove means just lose the thing or create the thing, create it on it. So let's say let's use the X and then the crate. You see how the X are resting on the crate, right? So the X are not fixed onto the crate because when you turn it, everything will fall from the crate. So when the photon energy is equal to the work function, so the X, it will create the electrons like how the X are placed on the crate. But let's say the X are fixed on the crate that when you turn, the thing will still be there. They are stuck to it. So in that case, you've not shined the photon on it. So the electrons are fixed on the material. Then when you send in the energy of the photon, which is the same thing as the work function, then it will just remove the bonding and the electron will still be sitting on the surface, like how you put your X on the crate. But then if the photon energy is now more than that of the work function, then is that like you taking one egg out from the crate, and you now create a space there. So that's the difference. So if the photon energy is more, it will create the electron from it and then give part of the energy to the electron to move away completely from the surface of the metal. But if it is equivalent to or equal to, it will just create the electron. It will just uh, remove the bond that is in between the electron and the material, but that electron will still be sitting on the surface of it. So the moving away is, or the moving is to give the electron kinetic energy, but the creating is can just like break the bond. So it's just about breaking the bonds between the electron and then the surface of the material. Have I answered you?
Yes, sir. Yes, sir. Thank you.
Okay. So now let's talk about stopping potential. To stop something mean to bring that into a rest. So you have something that is moving and you want to stop it from happening. So the electron is moving and you want to stop the electron. So you need some force. So we call it a stopping potential. The stopping potential is basically the minimum amount of energy that you need to bring the fast moving electron to a rest, to a stop. So something that is moving with a force or with an energy, and all of a sudden you want that thing to stop. So you need to get some energy to block it. Okay, so that's what we call the stopping potential. So this is the minimum amount of energy requires to bring the fast moving electron to a rest. Okay, so the energy that you need to stop the electron from moving is what we call the potential. So we can talk about the maximum. Okay, so no, it should be the maximum. So this should be the maximum kinetic energy, because that is the energy that the electron will be moving with. That is its highest energy. So you also need the amount of energy to be equivalent to that. So it means that the stopping potential is EV naught is equals to the maximum kinetic energy. So EV naught is equals to KE. So you have this as your stopping potential. So the EV naught is the stopping potential. So you need the V, that's the potential. Okay. The word is the potential as we know from the electricity, okay, voltage. But the E there is what the electric charge that we've seen. So if you are asked to calculate for the stopping potential, so you have to divide through by the value of the elementary charge, which is a 1.6 times 10 to the power minus 19 coulombs. So when you know the kinetic energy of the electron divided by the charge of the electron, and that will give you the potential. That's the potential energy. So E here is the electric charge. Then V naught is the potential. So you note the higher the work function, the higher the work function, the higher the stopping potential. Okay. Yeah, are we together? Okay.
Yeah. Mr. Can it be a case that the the potential will be given the electric was given they ask you to find the kinetic energy.
Come again.
Can they ask you to find the kinetic energy and they will give
Yes.
the potential and
Yes.
the electric charge? Okay,
Yes. So
anyway,
for the electric charge, nobody will give to you. You should know that it's a constant. So
constant.
they can ask, the question can come giving you the voltage that accelerate the charge, and they ask you to find the maximum kinetic energy. So you should know that, okay, what is the relationship between the maximum kinetic energy and then the stopping potential? So if they give you the stopping potential value, then you divide that by you multiply that one by if you are given the potential, you multiply that one by the electric charge, and that will be your kinetic energy. Can we move ahead? Okay. So let's see the results that Einstein got from the experiment. Actually, this was the experiment that he was awarded the Nobel Prize in the physics. All his discovery, he really got the Nobel Prize through the discovery of the photoelectric effect. So when he performed the experiment, these are some of the discovery he came out with. So just like experimental results from the Einstein. So experimental results. So he realized that one, only sufficiently energy light makes an effect. So here, the diagram that I sketched up here. So when he used the incident light, he realized that the incident light that has enough energy were the one that made an effect. So some with a lower energy didn't have any meaning. And This answer the question that somebody asked if the photon energy is less than the work function. Okay, so once the energy is lower than the work function, it doesn't make any impact or effect. So only sufficient energy light makes an effect. There can be an enormous intensity of light that is not sufficiently energetic and no effect is observed. So you can also have a light that has a higher intensity, but as far as that light has low energy, then it cannot ignite an electron. So you should also know that the energy of the electron is not as the same as what the intensity of the light. You can have a light with a higher intensity, but that doesn't mean that that light has enough energy or has the highest energy. So that's something you should also take note of that. So there can be anonymous intensity of light that is not sufficient energetic and no effect is observed. So the kinetic energy of photoelectric I was saying something here now that I've forgotten. So here, what is that? Yes, the ejected particles are called, yeah, this is the photon electrons. So let me add that. Got there and then I was lost what to say here. So either particles or electrons. So it came in mind. So ejected electrons or particles that have changed are called the photoelectrons. Photoelectrons. So the kinetic energy of the photoelectrons are independent. They are independent of the light intensity. Of the light intensity. Okay. Then the second observation was that.
So the first one can be like a low span count and high span count.
Come again.
I say the first one, yeah, like somebody who is giving more span, but they are not enough energy
Yeah,
to
yeah, sure, sure.
Uh,
That's a perfect example. So you can relate that to it. So the second observation was that the maximum kinetic energy of the photoelectrons for a given material for a given material depends only on the frequency of the light intensity. And we saw that from the equation. So you see that the maximum kinetic energy of the photoelectrons for a given material depends only on the frequency of the light intensity. So which means that what work best for a certain material may not be good for the second material for or the other material, because the materials, they have what different work functions. So let's say you have a copper metal or copper material. So if this is copper, and copper has a work function of maybe 5 electrovolt, then we have maybe aluminium. So let's say Al has maybe 3 electrovolt. So now if I have a photon which has an energy of 4 electrovolt, so you can see that this photon will be able to cause photoelectric effect in aluminium, but it cannot do that in copper because they have different work functions. Okay, so that is why the second point is saying, so what the maximum kinetic energy of the photoelectrons for a given material depends only on the frequency of the light intensity. Okay, so since the work function of copper is 5 and the frequency or the energy of the incoming photon is 4, then it cannot cause photoelectric effect for copper, but for aluminium, it can cause photoelectric effect and still give some energy to the electron to move away from the surface of the aluminium. Okay, so take note that the photon energy doesn't work for all set of materials. So it depends on the wave function of the materials. Now the third thing that he also observed was that the smaller the wave function, that is phi of the emitter. The emitter is the material. Of the emitter, the smaller its threshold. Its threshold frequency. Of the light that can eject photoelectrons. Okay. So this point is saying that, when you talk about a threshold, it's the minimum frequency, right? A threshold or something, this is a threshold. So it means that if you are able to reach that point, you qualify it. Okay. So if there's a cutoff grade for taking students for some which is post, let's say degree holders, teachers with degree. So it means that the threshold is what? Degree. So if you are a teacher and then you have a diploma, it means you are not qualified to be enrolled as a switch student. So that is the threshold of the program. So when you also talk about the threshold of the frequency, that would be the minimum requirement for the photoelectric effect to happen. So they are saying that the smaller the work function phi of the emitter material, then the smaller its threshold frequency. So it means that if the material has a very lower work function, then it also require a lower energy of the photon to be able to emit the electrons, just as the example I cited here with the aluminium and then that of the distance, the copper. So you realize that the aluminium was having a low work function, which is 3. So definitely we also require a lower photon energy to be able to eject the electrons. Now the fourth point is when photoelectrons are produced. However, when photon or photoelectrons are produced, however, their number is proportional to the intensity of light. Their number is proportional to the intensity of the light. Okay, so here it means that the number of electrons that are producing is the same thing as the intensity of the light. So if you are able to remove 2 electrons from the surface of the metal, it means that 2 electrons will correspond to the brightness of the light. So you are able to remove 10 electrons, then it also corresponds to the brightness of the light. Okay, but it doesn't depends on the energy. So number of electrons depends on the intensity. That is the brightness. The fifth observation.
Hello, sir.
Yes.
Lisa, how do you draw distinction between the intensity and the energy?
Okay. So let me come back to my first scenario I used with the location and then use easy. So let's say the energy is the fare. Now, how many people you are able to bring from their destination to Cape Coast? So if you need to bring 2 people, you need 200 cities. You understand? So as the number of people are increasing, then the value of the money has to also increase. So if there's one person, your aim is just like you should bring somebody from where the person is to Cape Coast. That is your target. So if you are able to do that, fine. But if you now have more money, so 100 cities, they say you have 1,000 cities. The 1,000 cities depends on how many people with this 1,000 cities is able to bring. You understand? So if 1,000 cities, it means that you're going to generate more people. You're going to bring more people. So you have more electrons being generated. And that electrons that are generating is amount up to the money you now have. How many times the money can carry the people here. You understand? So the intensity is just about the brightness. So when you have a light, uh, when you use the bulbs that we have in our rooms, see the bulbs are rated in terms of what? So the one that has a higher rating power, it means that it absorbs more electric energy. You know, electrons flows or current is obtained as a result of what the flow of charges. So it means that the more charges that are flowing in there, that gives you the brighter nature of the bulb. So once its rating is high, it means it is able to take more electrons at a time. Then the one that has a smaller or a lower rating will take less electron, and it will not bright as the one who absorbs much electrons. Is that okay?
Yes, sir.
Uh, so the brightness or the intensity just talks about how many electrons you are able to create from the surface of the metal. But the energy is just like the amount of energy you need to be able to create the or remove the electron from the surface of the metal.
All right, when we take. Thanks.
Okay, point number 5. The photoelectrons are emitted always instantly. So the photon or photoelectrons are emitted almost instantly. Almost instantly. Please, the rest of you, are you here at all? I'm only hearing one person's voice.
Sir, we are here.
Okay, that's fine. So we're saying that the photoelectrons are emitted almost instantly following the illumination that okay, illumination of the photodiode. Independent of the intensity of light. Okay, so the photoelectrons are ejected almost immediately when you ignite the diode. And as far as the diode has the energy equivalent or more than the work function, so the electron will also liberate instantly. It doesn't take time before it is able to do that. So the safe one is, so they also saw that there was a threshold frequency. A threshold frequency, which is F naught. And below this frequency, no photoelectron was ejected. Okay. So now these were the observations that he found in the experiment when he ignited a light on a source target to eject electrons from it. So he observed these 6 things that we've gone through. Okay, so now when he put these things in a graph, so let's say we have a material. Then the material, we plot a graph of the intensity. Oh, just a minute. Yeah, hello. Yeah, fine. Okay. So if we plot a graph of the intensity against the voltage, the applied voltage. So let's say we have our intensity in the y-axis and the applied voltage is here. So this is our intensity axis. Now, this is our potential here. Okay, so we have a graph of something like this. So we have something of this nature. So this is what we are going to have. Now, this will be the intensity I here. The intensity here, the first one intensity will be I naught. The second one intensity will be 2 times I naught. And this one will be 3 times I naught. Now here is the apply voltage. So at this point here, that's where we have our stopping potential. V naught is here. That is our stopping potential. So when you plot a graph of this nature, this is what you're going to have. So it means that the stopping potential will be constant, but the intensity is going to vary if you use a varying intensities. So it will be a discrete multiple of it. So you can see that as you increase the potential, so the intensity is increasing, but the stopping potential is constant. So here you can talk about the diagram here, same emitter. The emitter is the same material. So same emitter material, same emitter material, which has V naught, because once it's the same material, the stopping potential is same. Same kind of light. So that is same kind of light frequency with different intensities. Intensity. So you can see that when you take the same material and then you give the same light, that is the same energy, the photon, because the frequency is the same. So since it's the same material, you expect the stopping potential to be constant. So that's why you see that the curves, all of them are meeting at the stopping potential. They all have the same stopping potential here. So, but the intensities are varying, the same photon energy, but the intensity is increasing. So this tells us that the energy is independent of the intensity. Okay, so let's look at what we mean by photocurrent. Photocurrent intensity depends on the incoming intensity. The incoming intensity, if sufficient energetic light has been used. Has been used. So from the diagram there, the V naught is the stopping potential. Okay, so now when you plot the photocurrent, so let's plot the current against the light intensity and see what's happening. So this is the current I. Then we have the intensity here. So in this case, we have the voltage with proportional to that. So this will give us a linear graph. So here, you give us a voltage to be constant. So the voltage is constant throughout. So here too, the light has constant energy. Constant frequency or energy. So when you also plot the current that is generated by the photon against the frequency at the same energy provided, you have a linear current or voltage that is produced, okay, which is constant. So we can say here that the photon current is a linear function of light intensity. Light intensity if it is sufficiently energetic. energetic. It will overcome the work function. Okay. So let's also see if we take different emitters and then plot the current against the voltage, and the intensity against the voltage, see what will happen. So we are now taking different emitters. The first graph we saw was the same emitter, the same energy. But this time around, we are taking different materials. So material with different work functions, and then see. So our intensity is here. So now we're going to have this. Then this will come here, come here, come here like this. So here we have our first V naught for this one. So let's say on the device to extent. Okay. So if this is V naught, this will be 2 V naught. This will be 3 V naught. Then here we have the photo intensity to be constant. So the photo intensity is constant, but because we have different material, each of them has different stopping or work function. So we have a different stopping potential for them, but they all have the same work function. So this is the frequency. Let's say this for this material we have frequency F3. This one we have F2, and this one we have F1. So where the frequency of F1 is greater than the frequency of F2, which is in turn greater than the frequency of F3. So we plotted this one against the voltage. So when you have different materials, then with different energies, you will have the same intensity. You have the same intensity, but the stopping potential is going to vary. So this is what is going to, it means. You are at different locations. So if you are coming to write a quiz here means that all of you must travel from wherever you are. Some will travel a shorter distance, others will travel a longer distance. So at the end of it all, you all come to UCC, but others will be paying more money for transportation costs, and while others will be paying less money. So that is all. At the end of it all, you all meet here. So your meeting point here is a constant point. That will be the intensity. Then the stopping potential V0, V3, 2 V0, 3 V0 will now be depending on your locations, wherever each person is. Okay, since all of you are not at the same place, definitely you are not going to pay the same car fare before you get here. So you have different fares, a lot of fare to pay. So that's why we have different stopping potentials. All right. Any question, please? So the node under this curve is for 3 emitters materials or emitters, 3 kind of light frequency, frequencies, and are required to get a photo current. Okay. So that is the meaning of the graph here. Okay, so let's look at some metals with their work functions. So if we consider some metals in discovery or literature, they have the following work functions that are known. So let's say we have a material at the left, and then the work function at the right side. So we pick a sodium metal. So this will be 2.28 electrovolt. So sodium has a work function of 2.28. Then aluminum have 4.08. 4.08 electrovolt. Then calcium 4.7. Then we have zinc, and zinc is 4.31. Then silver. Silver is 4.73. Platinum. Platinum has 6.35. Then we have lead. Lead has 4.14. And then we have iron. Iron is 4.5. So these are some known elements with their work functions. So if you look at what we have here, platinum has the highest work function. So if you give a photon, if you shine a photon with energy that is 3, so it means that that energy or photon will only work for sodium, but it can't work for aluminum and then the rest, because the photon has an energy that is lower than the work functions of these materials. Okay. Now, what we've gone through is the modern interpretation of the photoelectric effect. Now we see why the classical mechanics couldn't explain the photoelectric effect vividly for us to understand, and there was a need for us to switch to the modern. Okay. So let's also look at the concept of the classical interpretation of the photoelectric effect. So classical concepts on the interpretation of photoelectric effect. So one, the difference is that for the points that we've gone through, for the classical, the modern concept, we saw that there was a threshold frequency. That was the last point or so. There was a threshold frequency, but in the concept of classical mechanics, they could not explain that threshold. That was it was missing in their explanation of this. So the first one that the faults or mistakes that they were having is the existence of the threshold frequency is completely absent in the classical theory. So the existence of the threshold frequency was absent. Completely absent. Absent in the classical theory. Now the second loophole was that the total amount of energy in the light rays increases as light intensity increases. So the classical theory, they were also saying that the intensity of the energy increases with increasing the intensity of the light. So the total amount of energy in the light rays increases with just a minute. The word is not responding. The PowerPoint. So okay. So the total amount of energy in the light rays increases as light intensity increases. Then the third challenge was so for extremely low intensity a long time will elapse. Elapse. Will elapse before any one electron will obtain energy to escape. So from the modern point of view, we saw that the electron leaves the surface immediately, almost immediately, when the potential is illuminated. But for the classical point of view, it takes some time. So for the electron to be able to leave the surface or to move away from it. So the observation that were drawn, photoelectrons are ejected almost immediately. That is from the morning. Photoelectrons. Photoelectrons are ejected. Just a minute. Okay, so let's just continue. So now the observation that was drawn from the classical, the modern point of view is that the photoelectrons eject almost immediately. Almost immediately. Immediately. And then the conclusion is was that like so light cannot be a Maxwellian. A Maxwellian wave, but must be a stream of particles. A stream of particles. However, light shows typical waves property. Light shows typically waves properties. In some instance. Example. Interference. Interference. Hence, light could either be considered, could either be considered as a wave or a particle. Particle, depending on the phenomenon. Okay, so this conclusion that is they're drawn from the influences from the two school of thoughts. Now, after comparing the findings from the classical point of view and then that of the modern physics, and the conclusion was that from the classical point of view, they was not able to make the distinction between the particular nature and then the wavelength nature of light. They know that light is only exists as a particle, but from the experiment conducted by Einstein, also realized that light indeed is a particle, but it can also behave as a wave. Uh, so the modern is able to let us understand that light has a dual nature. So it can behave as a particle at the same time as a wave. So that is the distinction between the classical physics and then the modern physics in conjunction to the photoelectric effect. Okay, so that is it for photoelectric effect. We'll get some trial questions, some examples, and then solve them. So now let's look at the Einstein prediction about the photoelectric effect. Albert Einstein's theory. Okay, so one, he predicted that EM radiation, that's electromagnetic radiation. EM radiation field is quantized. It's quantized into particles. Called photons. Called photons. And each photon And each photon possesses the quantum of total energy. Possesses the quantum of total energy. Total energy, which is all kinetic. All kinetic, as they do not have mass. So here that Einstein predicted that photon is a massless entity. Photon is massless entity. And because of that, it changes the definition of matter as we used to know. We used to define matter as what? Anything that has mass and volume and can occupy space. But because of this concept, you cannot define that definition for matter and expect it to be correct. Because if you say matter is anything that has mass and volume and can occupy space, what about a photon, which is a massless entity and can also occupy the space or can also be classified as matter? So that definition was redefined as matter is anything that has volume and occupy space. So photon has a rest mass. So it's a massless entity. It has no mass. So that's why I say that it is all kinetic. So all kinetic means that it moves with the speed of light and has zero any mass. So it's a massless photon moves with the speed of light. Moves with the speed of light. Okay, so now you can write this energy as here. So the E is equals to HF that we saw, which is the same thing as HC over lambda. Then when you want to write this in terms of the quantum aspect, so we can write this one as this omega. So where the H cross bar is equals to H bar, the H over 2 pi. I think I've stated this one earlier. Okay. So when you are dealing with the quantum aspect of the physics, at that point where we are now leaving the classical meaning of the physics to the microscopic level, then we write our frequency. So either nu or when the particle is moving the speed approaching the speed of light. So the frequency can change to nu or omega. So in that case, we write the photon energy as E is equals to H cross bar omega. So that is the quantum physics. If you are writing the energy of the photon in the quantum physics, you use the second equation, but the point of classical, you can still use this. But at this point, we are presuming that the energy is purely kinetic. So it is moving with a speed closer to that of light. So the second prediction by Albert Einstein. So the second one is that the photon travels in the speed of light. In the speed of light, c, in a vacuum, that is in a space. In a vacuum, defining the wavelength lambda. Defining the wavelength lambda. Lambda and the frequency. F as. So the C is equals to F lambda. So that is also the relationship between the speed of light, the frequency, and that of the wavelength. Okay, so let's continue. Now let's look at the third prediction. So the third one is that the conservation of total energy. Total energy yields the following equation. Yeah, so in everything, always try to conserve energy so that our analysis can be right, because you can't compare two things that are happening wrongly or are not happening the same thing. So you try to see, as you subject energy to the system, you don't expect the energy to be lost, since we know that energy can neither be created nor destroyed. So we try as much as possible to conserve the energy. So if you are saying that the photon is coming in with a certain energy, and this photon strikes the surface of the material, then that photon energy shouldn't be lost. So the energy should be converted to something else. So by if you combine those things that happen within the system before the collision or the striking, then you still get back the same energy that was subjected to your system or was put into your system. Okay, so through the energy conservation principle, we're saying that the energy before should be the same thing as the energy after whatever that has happened. The energy that you have, it should be the same thing as the energy that you will obtain after whatever has happened. So now the energy, which is HF, should be equals to the work function plus the kinetic energy. So it means that when the photon hits the surface of the metal, part of the energy of the photon is used to balance the work function, and the remaining energy that is left will give the electrons kinetic energy to move away from the surface of the electron. Okay, so now we define these terms already. You know that the phi is the work function, The K is the kinetic energy. So I can still say that my HF will be equals to my phi, and then plus my K. Now let me substitute the definition of the kinetic energy. So kinetic energy is expressed as half mv squared. And your V should be at its maximum. So you are dealing with the highest energy because that is the highest velocity that the electron will be moving with. Okay, so take note of this equation. You'll be using it. Then the fourth prediction. Now the retarding, that is the stopping potential. Yeah.
I will say,
Uh-huh.
listen, so HF is equals to the phi half mv squared. Here, the mass, is it going to be a mass of electron?
Yes. It's the mass of the electron. So you have to, because we are saying that if the energy of the photon is maybe, let me say, 3 electrovolt, then the wave function is 2. The wave function of the material is 2 electrovolt. Now, this 3 electrovolt, 2 of it will be used to counteract this work function. Then the 1 electrovolt that is left will be transferred to the electron to move. So it means that you're going to have 1 electrovolt to be equals to the mass of the electron, half times the mass of the electron, times the velocity that the electron will be moving with. Okay, so the m is the mass of the electron, the velocity, the v is the velocity that the electron will be moving with.
Okay, sir.
Yeah, you're welcome. Okay, so the retarding or stopping potential measures. Measures in the photoelectric effect. The photoelectric effect are the opposing potential. The opposing potential need to stop, needed to stop the most energetic photons or the most energetic photon. And so that's why we have the EV naught is equals to half mv squared. And v should still be the maximum velocity. So the next of his prediction is that the kinetic energy of the electron does not depend on the light intensity. So you should also know that the kinetic energy of the electron does not depend on the light intensity. but only on the light frequency. And the work function. So you can write that the kinetic energy, which is half mv squared, to be equals to the stopping potential, which is the same thing as the photon energy minus the work function. So when you know the kinetic energy, you can calculate for the stopping potential. If you also know the difference between the photon energy and then the work function, you can also calculate the kinetic energy or the stopping potential. Okay. So last study, we are saying that the stopping potential, as I said, the stopping potential is linearly proportional to light frequency with a slope h, which is a Planck constant. Planck constant. Okay. So what he meant here is that if you take the stopping potential V naught should be equals to half mv squared, and this should be same thing as h f minus h f naught, which is the stopping potential, and this is the same thing as h open bracket f minus f naught. Okay, so that is what Einstein is saying. So when you plot a graph, of this. Now here we have the stopping potential EV naught, and this is against frequency. So he is saying that you should get something like this. So here will be your V naught. Here will be your F naught, sorry. Here will be F naught. And here will be your F. So now at this point, we have a negative intercept. So here, the intercept here will be negative of the work function. So now, when we use the formula that we had earlier, we saw that the HF is equals to the work function plus the kinetic energy. We saw this equation. So now, if you plot a graph of the stopping potential, but we also know that the stopping potential, EV naught, is the same thing as the work function. Okay, so if you make the work function the subject from the above equation, so it means that we have the work function, which is equals to the HF minus the kinetic energy. So we have this one there. Okay, so now we are saying that the material has a threshold frequency. So that threshold frequency will be the kinetic part. So if we substitute that, so we're going to have the HF minus HF naught. And when you plot this graph, you have this one there. And the intercept is going to be the work function, which is a negative intercept. Okay. Any question, please? Are we following the discussion? So F naught is the minimum. Are we there?
Yeah,
Yeah.
So, or we are tired?
we are there.
Like we are tired, right? So F naught is the minimum amount of energy. The minimum amount of energy. So don't be confused with the F naught. And then when we say we are using F as energy because they are directly proportional. So the energy is proportional to F. When you introduce the constant, that makes it HF. Okay. So you can use the word energy or frequency, they are the same thing. Okay. Because they are directly proportional. The H is just a constant. So F naught is the minimum amount of energy needed. Okay, can you mute yourselves again? Needed to eject. I'm not sure this person is paying attention to the class. Mr. Francis Governor.
Say,
Okay, then you're not the one. As I can hear some background noise, but your microphone is also on. I thought you were the one. Okay, thank you. Okay, so we are saying that the F naught is the threshold frequency or the minimum amount of energy needed to eject an electron from the surface of a metal. From the surface of a metal, but leaves it with zero kinetic energy. Leaves it with zero kinetic energy, which means that if it is equals to F naught, you will be able to create the electron, the bond, all right. But that electron will still be sitting on the surface of the metal. So that is to mean that you leave the electron with zero kinetic energy. The bond is broken, but the electron cannot move. And remember, we are doing this with the purpose of what? Generating current. And current is obtained as a result of the movement of what? Charges. So when you break the bond and then your charge is at rest, there's no way that you have current being generated. Okay, so you take note of the point that when you have an energy which is equivalent to the work function, then you don't have current being generated by that effect. So 7 says that light consists of particles with energy. Light consists of particle energy. E is equals to HF, which is the same as HC on lambda. That's the Einstein prediction. Okay, so we plot the Milton's experiment of the frequency against V naught. So you have something like this. So you can find this slope from here to give you a positive slope. Okay, so now these are the theory behind the new revolution that happened, and the name was coined as the modern physics. So at least we have done about two concepts that could not be explained by the Pascal theory. One is the black body, and the other one is the photoelectric effect. Okay, so we are moving on. Let's look at our time is up, right? Maybe we are close now 3 or
4.
4, say.
4.
Yes, sir.
8. That is 3 oh.
It's 4.
Oh, okay. Then let's continue. I was thinking it's 3. I thought. Okay, then let's look at some examples. Examples. Okay. We still have more time, 1 hour more. I was thinking we have few minutes to go. Okay, let's solve some problems here. Examples. So the first question is, in the photoelectric effect, in the photoelectric effect, what happens to the energy of the photoelectrons? The photoelectrons as the wavelength as the wavelength of the light increases. Okay, so this is a question then 2. A. What is the threshold frequency for photoelectrons? For photoelectrons from lithium. From lithium Li with work function of 2.9 electrovolt. Oh, who is this? Somebody is calling me. Let me come. I don't know the person. All right, so let's continue. Sorry about that. Okay, so we are saying that what is the threshold frequency for photoelectrons from lithium ion or lithium with a work function of 2.9 electrovolt? And then B, what is the stopping potential? The stopping potential if lambda is equals to 400 nanometer is incident on it. Incident on it. So in other words, if light of wavelength 400 nanometer is used or is incident on the material lithium, then C of the question. What is the maximum kinetic energy? What is the maximum kinetic energy of an electron ejected by this wavelength, of an electron ejected by this wavelength? Then finally, what is the maximum kinetic energy? Okay, that's what. Calculate the maximum velocity of the injected electron. Calculate the maximum velocity of the ejected electron. Okay, so let's ask some few questions before we see how we are going to. So let's say the third question here. Question 3. Sodium has a work function of 2 electrovolts. Calculate the maximum kinetic energy and the speed emitted by emitted when sodium is illuminated with light radiation of wavelength Yeah, correct. Yeah, good afternoon. I'm not known elsewhere. So the radiation of wavelength of wavelength 150 nanometers. First stop. Then what is the least frequency? The least frequency of the radiation for which the electrons are emitted. Okay. So by this question, the constants are, you take H to be equals to 6.62 times 10 to the power minus 34 joules per second. No, it should be joules second. Then 1 electrovolt is equals to 1.055 times 10 to the power minus 31 eV. And then the charge of the electron is equals to 1.6 times 10 to the power minus 19 coulombs. Then mass of an electron is equals to 9.11 times 10 to the power minus 31 kilograms. Then the speed of light is equals to 3 times 10 to the power 8 meters per second. Okay, so fourth question. Find the energy of a 700 nanometers photon. Then 5, find the wavelength and frequency. And frequency of 100 mega electric volt photon. And then lastly, question 6. A 1 kilowatt radio transmitter operates operate. So it operates at frequency at frequency 880 kilohertz. So kilohertz, how many photons per second does? Per second does it emit? Okay. So these are some trial questions that we need to go through.
Mr. Go back to question 5. Let me see. I didn't see that.
Okay. So question number 5. Will you wait? I'm saving it, so let it finish saving before I can. If not, I can't. All right. So question number 5 is here. Find the wavelength and then frequency of 100 mega electrovolt photon. 4 is find the energy of a 700 nanometer photon. Then when you come to the rest of the questions, question 3, you have a sodium ion or element that has a work function of 2 electron volts. Calculate the maximum kinetic energy and the speed emitted by the element if it is illuminated with light radiation of wavelength 150 nanometer. What is the frequency of the radiation for which the electrons are emitted? Then you come to the 2D, calculate the maximum velocity, so, and then the rest. Okay, so let's see. I'm not going to solve all of them with you. Try it yourself. The first 2 electron volt. Okay. Now the first question is that in the photoelectric effect, what happens to the energy of the photons as the wavelength of the light increases? So let's discuss this. What are your summations to this?
Hello, sir.
Yes.
I think with regard to that one, I think the photoelectron decreases as the wavelength increases.
Okay.
Because if you look at the this thing you gave first, E, when you have E equal to the AC over lambda.
Okay.
Assuming that with the E, which is the energy, is proportional to that of the wavelength, is the lambda. So as the other one increases, this one also
Yes,
increases.
inversely. So you use the word inversely proportional.
Inversely
Okay.
proportional.
So that is how you answer it. So you look at the equation and then you write your grammar to it. So increasing the question is in the photoelectric effect, what happens to the energy of the photoelectrons as the wavelength of the light increases? Okay, so you can infer the formula, or you can state it and then bring the formula to back your argument. Okay, so increasing the wavelength, we actually decrease the energy of the photon because they are inversely proportional. Okay, so that is fine. Then let's go to the second question. Now, the second question is saying that the first one, what is the threshold frequency for photoelectrons from lithium with wave function of 2.9 electron-volt? So it means that what is the minimum frequency that you will have, or minimum energy that you will have for photoelectric effect to be able to occur in this material. Okay, so solution to this. So solution here. So that is question number 2. Now we know that the work function is defined as H times F naught, where F naught is the threshold frequency. Okay, so now you are given the F naught was given right in the question.
Yes, please.
That's what we are finding. Okay, work function was given.
Work function.
Okay, so it's equals to 2.9 electron-volts. Okay, so since you know this, then you can make F naught the subject. So it means that your F naught is equals to the work function divided by the Planck constant. And this will give you 2.9. Yes, so now if you look at the constant that I've given to you here, you see that the Planck constant has a unit of joule. Joules is a unit of energy. Electron-volt is also a unit of energy. But you must work with one. So you either leave your answer electron-volt or you leave your answer in joules. So when you are dealing with an objective question, when you solve using joules and the possible answers, maybe your answer is not there, means that you have to try converting to electron-volt. Maybe you look at the unit of the answers provided. If the unit of the answers provided are in electron-volt, then you have to convert your answer from the joules to what? Electron-volt. If you also decide to solve with electron-volt and the possible options, you also have it in joules, then you have to convert from the electron-volt to the joule. Now the conversion is that 1 electron-volt is equals to 1.6 times 10 to the power 19. So you have to multiply by the charge of the electron to convert it to joules. Okay, so the 2.9 electron-volt that you have, if you want to use this, so now this one should be multiplied by 1.6. So this is the same thing as 2.9 times 1.6 times 10 to the power minus 19, and this time around you have it in joules. So it means that you've changed from electron-volt to what? Joules. So we have here times 1.6 times 10 to the power minus 19. Then all we now divide by, we have 6.62 times 10 to the power minus 34. Okay, so if you don't change the electron-volt to joule, you cannot use the 6.626, because if you don't do that, you're going to have electron-volt and then joule. So your unit is what? Inconsistent. You get your final answer to be wrong. So you must change it to either work with joules or electron-volt. Okay, So we have this. So you simplify those with calculators. Let's see what you have.
So I have 7.01 times 10 exponent 14 x.
So it means that the frequency should be 7 times 10 to the power 14 hertz. So this is your minimum frequency. If nothing at all, you should always be looking at the unit, the index 14 when you are dealing with the photon. The frequency should always be having an index around 14. Is that okay? So this would be your threshold frequency. Is that all? Okay, just a minute, I'm coming. Okay, so let's move on to the second question. So the B part of the question is saying that,
It's just a quick one.
okay,
The Planck constant in the the electron volt.
in
Is it for
the
that? For,
the
yeah.
contacts, the
Yes. If you want
constant
to change it
electric.
to
Okay,
yes. If it's in EVO, is it 4.136 times 10 raised to the power 15
is it
minus
what?
15? 4.136 times 10 raised to the power minus 15.
1.136.
No,
Okay, multiply
4.
multiply the 6.62 times 10 to the power minus 34 times the 1.6 times 10 to the power minus
19.
19. Let's see what value you get.
Listen,
Yeah.
if I heard you well, did you say we have to always get the exponent in terms of threshold frequency to be 14? Do always?
Yes. In terms of this context, when you are dealing with
Photoelectric.
photon, you should be looking around that. The frequency should always have a step of 14 around that. Shouldn't be something lesser than 14. At least when you have a number maybe times 13, 12, it's dealing with like the terahertz range.
Okay.
Yeah, when you multiply, what value are you getting?
So my calculator is giving me 1.0592 times 10 raised to the power minus 42 EVO.
It's
I don't know that.
1.0.
Yes, 1.0592.
Okay, then let me check. Maybe I've written. So you can forget about what I've written, but the correct way is to just multiply. If you want to change from one, if I change it from electron-volt to joule, multiply by the charge of the electron. If I change it from the joule to electron-volt, divide by the charge of the electron. So that is all. It should be 40. You said it's what? Raise the power.
Yeah, raise the power minus, I think 42.
Minus 42. So this should be minus 42.
I
And
want
this
to
should be,
divide it in.
so this should be H. This H in electron volt. Okay. Now divide this one by 6.626 times 10 to the power minus 34 by the charge of the electron. And then you get the value.
Okay, sir.
That is what you should have. Let me discard this.
Then you get the, I think 6.27 times 10 raised the power. This 7
You know what? Let me get the value again.
6.27
6.
times 10 raised the
Uh,
power minus 7.
let me come. 6 point
27
27 times 10 to the power
minus 7.
minus
Is it
7.
positive?
So this will be electrovolt. What I've written will be the reduced Planck constant. The first one that a 1.0 something will be the reduced Planck constant. That's the H cross. Okay, so let's go back to the solution side. So down the B part, talk about the stopping potential. Question 2B. So 2B says the stopping potential, and so you should know that the stopping potential is EV naught. So the EV naught is equals to the photon energy minus the work function. Because we said that HF is equals to phi plus kinetic energy, right? And we said the stopping potential is the energy you need to bring a fast moving electron to a stop. So it means that the stopping potential is the same thing as the kinetic energy. Okay, so it means you can write it this way, because if you make kinetic energy in this equation, kinetic energy will be equals to HF minus the work function. Then we substitute kinetic energy in place of the stopping potential. So we have this equation. So use this equation to solve it. Now, here, we need it's not the EV naught that is the stopping potential. The potential is actually the V.
Yeah, so I'm confused about
Rest on that. I think I've explained that when I was doing it. So you have to find V naught, not EV naught. So what do? You divide through by E. So if you divide through by E, it means that our V naught will now be equals to HC
HCG
over lambda E, then minus phi divided by what? E. So you have to divide both sides by on all the terms by E. So now we make our substitution here. We can now substitute V naught to be equals to the HF is going to be 6.62 times 10 to the power minus 34. This is multiplied by the speed of light. That's 3 times 10 to the power 8 divided by the wavelength was given. What was the wavelength in the question?
400 nanometer.
Okay. So the wavelength was given as 400 nanometers. So here, lambda is equals to 400 nanometer, which means that it's 400 times 10 to the power minus 9 meters. So that's what you're going to use. Okay. So this will be divided by 400 times 10 to the power minus 9 multiplied by the charge of the electron, which is 1.6 times 10 to the power minus 19. Then the next term minus the work function was given as what? 2.9, right?
Yes, please. 2.9.
So that will be 2.9 times 1.6 times 10 to the power minus 19. That is by converting into joules. And this one will now also be divided by 1.6 times 10 to the power minus 19. So this will cancel this. Then you multiply the first term, and let's see, multiply the numerator and then the denominator. Do it one separately. So this will give us what? This is 6, 18, 8. Then you have 18. So that would be 19.82. Am I right? 19.82 times minus 34 plus 8. That would be around like 26. So 26 times 10 to the power minus 26. Yeah.
It's like you get 1.936 times 10. You
1.9.
multiply with the 1.986
So
times
this
10
one
to
should be
the power
25.
minus 25.
This one should be
Yes,
25.
so
Right? Okay.
there is a power 25.
So this one should be minus 25. And this should be 1.98.
Yes, sir.
1.98 to the power 25. Then divided by 400 by this. Yeah, so what we have? $400.
You will get the denominator will give you 6.4.
You get what?
6.4 times 10.
That's 10,
That is the power minus 36.
36.
Yes, sir.
Okay. So now divide 1.982 exponent minus 25 by the answer that you had. And let's subtract 2.9 from it. So our V naught will now be equals to Mm-hmm.
Is it 0.2 electron volt?
There was 0.20
electron volt.
everything. Do you mean everything or what?
Yes, sir.
I wanted you to do this first time before we subtract. I want to get the values for the 1.982 times 10 to the power minus 25 divided by 6 point that. Let me get that value. So this will be positive. 36 is greater than 25, so it will give you positive 11. Where's the power 11? Then 1.982 divided by 6.4.
So
Uh-huh.
I had 3.0968 electron volt. So approximately 3.10 electron volt.
It should be half an exponent times what?
Times 10 exponent 10.
10 to the power 10.
Yes, sir.
It's not right too. Because if you look at it here, you have 25 and 36. If you subtract 25 from 36, will you get 10? Yes, okay, it's 11. Or
I said, so please, even the 36, the 6.4 times 10
that's
to the
correct. Okay, so that is correct. So this now minus 2.9, right?
Yes, sir.
Okay, so let's get the final answer. If you don't do it well, you can meet the same question, but because you compute wrongly, you wouldn't be able to do it. When you subtract 2.9 from it, what are you getting?
Sir,
Use normal calculator, no phone.
3.096 times 10 to the power 10.
3 point what?
3.096 times
No,
10.
you've not subtracted the 2.9 from it. This minus 2.9. What you are mentioning minus 2.9.
Okay.
So the final answer. So what's the final answer, please?
Please, I'm on it.
But please, you get like calculators. If you're using a phone, you might get.
I'm using real calculator.
Okay. I'm not having a calculator here. If not, just...
hello, sir.
Please, sir, I'm getting the
Yes,
same thing. Oh.
you're getting the same thing.
Yeah, 3.096 times 10 to the power 10.
Okay, so 3.096 times 10 to the power 10, and then is volt because it's a potential. So let's assume that the figures that you mentioned are right. So this will be your answer. If you compute the wrong value, then I'm not the one that solved it wrongly. Okay. So that is the stopping potential for that scenario. So let's go to the C part. This is the B part. So we are moving to the C. Yes. If somebody wants to say something.
Sir, please, so
Yes.
I also choose another way of solving it, but the answer I'm getting.
What did you get?
Sir, I got a 0.20 electron volt.
0.20.
So I use the energy equals to the Planck constant times C over the lambda, and then I got 4.969 times 10 exponent negative 19 joules, and then I convert it. So in electron volt, I divide my answer by 1.602 times 10 exponent negative 9. Then I had 3.10 volt, and I subtracted from the 2.9 volt. Then I had a 0.2 electron volt, but I don't know whether I myself is wrong there. And then
No, like you are not. So you worked with your answer is in electrovolt. What you are having is in electrovolt. Let me come. Let me go to the where I write. So your answer is what? 0. What?
2
29.
electron. Yes, my final answer is 0.20 volt electron volt.
20. No, okay. It should be something closer. Now, this is electrovolt. Okay. So if you multiply this one by 1.6 exponent 19, what are you going to have? Oh, no. This, you shouldn't leave your answer in volt, electrovolt. It should be volt. Your answer should be volt. So when you leave it in electrovolt, it means that you left it in a form of energy, not potential.
Okay, sir.
So maybe let's say which one talks about energy? I think the B part, right?
Yes, sir.
So let's see the B part, what we will have. Maybe that is what you have calculated. The C part, sorry. What you had is the C part. You'd rather solve for the C part.
Okay. Yes,
so let me leave your answer and we solve the C and see what answer we will get.
Yes, sir.
So now the C. What is the question? The question, where are you? The C.
What is the maximum kinetic energy of an electron ejected by this wavelength?
Okay. So the maximum kinetic energy. Maximum KE. So the same way you use a formula, your KE is equals to HF minus the work function. Okay. So minus the work function. But always remember that the KE is the same thing as the stopping potential. Okay. So if you get a KE, it means that you can talk about the stopping potential. Okay. So now our KE will be equals to 1.6 times 10 to the power minus 19 times what we have. I suspect this answer shouldn't be like that. Let's see. So,
yes, I also think when we were coming, we had something wrong there. That is why.
let me come. So let me assume that what you have here
If
is
possible,
right.
can we all go through together again?
So you have this. So if your answer is correct, so this is how you solve it. So let's go back. Let's go back to how we solve the B. Like the values there are not right. So the B
Hello,
is
sir.
yes.
With the B, I think when you multiply the 400 by 10 to the power minus 9 by 1.6 times 10 to the power minus 9,
Mm-hmm.
I had the exponent to be 26, but it is 36 here.
It's 19. No.
Yes, the 19.
Oh,
So
it's
I just
26.
it's,
Yes.
it's 26.
Yeah, that should be 26 because
26.
19 plus 9 is 28.
Yes.
Then
Yeah,
this
but I think we
400
have
is 0.
36. We
Yes.
have
So
36 there.
I think that's where the problem is coming. So this one
Yes.
should be 26.
Yes. So
So 26 here. So let's recomplete our value. So 26 here. Okay. So 1.982 exponent minus 25 divided by 6.4 exponent minus 26. And let's see what we get. So definitely this will change.
I had 3.0967875 electron volt.
6.0968
68 electron volts.
pretty sure times 10 to the power
times
minus 52.
minus what?
52.
I can't hear the value.
52.
52 for real. Let's see. It cannot be 52.
Okay,
You
we
see,
have
this is minus. So when you take the
minus
minus
25.
out, it becomes positive.
Eh,
Okay.
So when you are adding them, that if they are all minus, that you get a huge value.
Big on the minus.
So that is the value that you had, right?
yes, sir.
Okay. Then if you now subtract these two, what are you going to have? So it means that there is no exponent there.
Yes, sir.
So let me erase the exponent. So you subtract 2.9 from it.
I had 0.196875.
0.19. So this is 0.19, right?
Yes, 6875.
6875. Okay, 6875. Let me just leave it there. So volt. Okay. So now we are here. So we are here now. Our kinetic energy. So multiply this one by the charge, by the answer that we had up there. See what we're going to get.
Sir, please,
Uh-huh.
with regard to the 3.0968 electron volt minus 2.9 electron volt, and the answer is volt. That is where I was a bit confused.
No, the answer wasn't in the volt. Let me show you. You see from here, look at what we were having here.
Okay.
HC over lambda minus phi. And then phi was given as 2.9, right?
Yes, sir.
And then 2.9 was in electrovolt. So we change it to joules. So that is by
Okay.
multiplying by electron volt. So this one has a charge here. Come to this side. Can you see my cursor?
Yes, sir.
So you see that we have 2.9 because of the electron volt. We multiply by the charge of the charge. Then it's divided by the charge here. So this and that cancel out.
Okay.
So when they cancel, I have 2.9. Then when you come here, so this is 6.6 times this and then that. Also check this one and let's see. Confirm this one and let's see what we're going to have. 6.62. The answer we are getting, it should be, it still have something raised the power.
So this one I had 1.986 times 10 exponent negative 25.
Okay. Okay. Yes. Okay. So, well, that is how we go about it. But you check the values to confirm whether they are correctly computed. But that is the procedure. Now, when you come to the, where's that come? When you come to the maximum kinetic energy, so you equate the kinetic energy to the stopping potential, and you make the kinetic energy the subject. That's also for the kinetic energy. So assuming the value that we got for our stopping potential is correct in E, so we're going to multiply that value by the electric charge to get the maximum kinetic energy, because the maximum kinetic energy is the same thing as the stopping potential. Remember, we define it as what? The amount of energy that you need to bring the fast moving electron to a rest. And so before the stopping, like if your stopping potential energy is not measured up to the energy that the electron is moving with, you can't stop it. So just imagine that, like, you fired a gun and you want to stop the bullet of the gun. So it means that you need energy that is equal to the energy that the bullet is moving with, so that you can stop the bullet at instant. If not, it will penetrate whatever you put. Assuming like you're using some energy that is lesser than the energy of the bullet, it will pass through that thing and then still be moving. So it means that the energy it requires is the same thing as the stopping potential, and you use that relation. Get it? Okay. So that is that. Then you solve the remaining questions. When we meet next week, we will discuss them. Please go through them. The last week one, I don't know whether you've gone through them or not. Let me
Yeah.
send you this the notes
The
before.
recordings, they have not come.
The last one I think we went through, but the last question, the drawing, that is a little bit confusing.
Okay.
The one you said
You didn't say anything. I wanted us to look at it before we. So next week when we meet, we will discuss them. So, but go through them. It is for your own good. If you go
So
through
Doc,
them and then understand them, it's fine.
the one we just work, let's see. That means that if you get if your first the B the V is wrong, that means that it also affect the C, right?
Yes, because you are doing direct substitution, you will also get it wrong.
Okay.
I'll also get a calculator and then compute it here, and then when we meet, and then there is a problem.
Well, the V note, the answer is wrong.
It's wrong, eh?
Yes.
Yeah, because you still have something raised the power. Okay, so let me send this to somebody. Someone should send me hi, and then I'll forward this one before I leave. If not, so me, I want to leave now. Forget that I've not sent you the thing. So this is what I will do. I will send you everything. So when we meet next week, after that, I will send you a complete of the previous weeks. So if you want, you can delete the one that I'm sending you today, so that you can make room for more storage. Because I will continue from the very beginning. Okay, so if I send you the current one, you can delete the old one, and then the current one contains everything that you have.
Okay, so I've sent hi on the 84.
Let me see. Let's see. Let's see. Let's see. Oh. Okay. So when I send it, I don't know whether you have a separate group you put it there for. Who is that? The person should come. Yes, come. Yeah. Oh wait. Just a minute. Okay, I'm coming. Let me. Yeah, have you received it? Okay, it's still loading. So that's it. That's it. Yeah, it is still loading. So you receive it.
Okay, sir. All right. So when it comes, I'll forward it to the platform.
So you go through them. What will be next week? We'll meet and then see.
Rado, thank you very much. Bless you.
You're welcome.
Straight 4 hours.
So
Not easy.
if there is no more questions, then we'll pause here. Please, we are tired. Yeah, it has come.
Okay.
All right. So bye for now.
All right. Bye.